Welcome everybody to our CAPMA seminar. Today we have the pleasure to guest Ángel Martínez-Muñoz from the Universitat Rovira i Virgili, who is going to talk about pairs of forms in geometric mechanics. So thank you, Ángel, for accepting our invitation. It's a pleasure to have you here. And
Thank you.
let's go on. The floor is yours.
Okay, so thank you very much. I'm very happy to finally be speaking here because I've been listening to a lot of your talks. And yeah, I'm just very glad to be here presenting this. So as Javi said, I will be talking about pairs of forms, and in particular, I will talk about the applications to geometric mechanics. And this talk is based in a preprint that we published in February with my two thesis supervisors, Xavier Gracia and Xavier Rivas. And yeah, so I'll be starting. This is a little bit how I've organized the presentation. So basically we'll be reviewing the whole paper if I have time. And I will begin with a little introduction, some motivation. Then here I will give the basic definitions and the main theorem and some of the most important results. Then here we will see some objects that are naturally associated with the structures we care about. Then I will be giving a few examples. And then at last, if I have the time, which I hope I do, I will be telling you about these changes of parity, and you will see later. Okay, so what are we going to do? Well, basically, we were studying singular Lagrangians in contact mechanics. And there were some cases that weren't studied very much because you didn't have some red vector fields and stuff. So the geometry there wasn't very understood. So in trying to understand that, we found out that there was a little bit of a hole, we believed, in the literature when talking about just pairs of differential forms. So what we did is take a one form and a two form and say, okay, what can we say about this? What are the main properties about these pairs of forms that we say? And well, this is very important because a lot of geometric structures in geometric mechanics are formed by a one form and a two form. So probably as you all are very knowledgeable in this topic, you will some of these names will sound familiar, right? So symplectic geometry, there you have a two form. In cosymplectic geometry, you have a one form and a two form. In contact, you have the one form eta and then it's differential. So again, you have a one form and a two form. In locally conformally symplectic geometry, you have a non-degenerate two form, and you also have this Lie form. I'll explain the example later. But well, these are structures that appear a lot. So it's important to have a framework to explain them well. And this is what we'll be studying. Also, one of the, I think, most important things of this preprint was to associate dynamics to these pairs of forms. So, for example, when you're dealing with contact geometry, there's this very important vector field, which is the Reeb vector field, right? So, where does that come from in a more general way? That's what we try to answer. And when you don't have Reeb vector fields, which is the case that we were studying originally, what happens? What do you have there? What would be the analog of that? That was one of our questions. And so, yeah, we try to do this, just give a general framework to study these geometrical structures. So first of all, let me give you a little bit of an introduction, a little bit of the main definitions for this subject. So given a P form, the kernel at a point is just the kernel of the induced map that takes vectors, right? And so it's just this. And then the rank of a form is just the codimension of this kernel. So it would be the rank of the linear map induced by the P form just by taking a vector. And this matches the dimension of the annihilator of the form. So I will just recall here the annihilator. The annihilator would be all the covectors such that they are zero when contracted with something that's in the kernel, right? So you would have this definition here. And as we are focusing on the case of one forms and two forms, it's important to study this this kernel for these specific cases. And it's very interesting that they are very restricted, because if we have a P form, one form, sorry, so P equals 1, then the annihilator of the kernel is just the form. So either the rank is 1 if the form is non-zero at that point, or the rank is 0, right? So this is just multilinear algebra. And then if you have a 2 form, then the interesting thing is that the rank is always even. So at every point, the rank is even. It might change, right, at different points, but the rank will always be even. And also you have these sort of algebraic conditions that tell you what the rank is. With this notation, what we mean is just taking the wedge product R times, in case you're not familiar with that. And yeah, so you have this sort of classification of the rank. So now, if we want to study these pairs, so we want to study the relation between a 1 form and a 2 form, it will be useful to introduce this notion, which is the class. So this notion is similar to that of the rank and the kernel, because we will define first the characteristic distribution. This is just, you take a P form and a Q form, and you take the intersection of their kernels. And then the class, similar to the rank, will be the codimension of this distribution. Also, it is the dimension of the annihilator again, right?
Excuse me, this
Yeah.
may not be a regular distribution. You are assuming the class to be constant.
Yeah,
It's
sorry.
constant, right?
Yeah. Well, right now I'm just talking like at a point, but yes, we will assume that they are all regular distribution. I think it's in the next slide. Yeah, sorry. So right now this is just at a point. So let's say it's a vector space, right? You have this vector space, and then you take its codimension at a point. But yeah, it might change. It might not be regular, the dimension. So well, note that the annihilator of this characteristic distribution is just summing these two vector spaces. The sum might be a direct sum or not. This will be important. So yes, I comment here, from now on, we will just consider a 1 form and a 2 form. So even though these definitions work for general forms, we will just restrict ourselves to having a 1 form, which I will call tau for the rest of the presentation, and a 2 form, which I will call omega for the rest of the presentation. And we give this definition, which is what Asier commented just now, which is that a pair is a doublet if the class is constant. So the class the class being constant is equivalent to the characteristic distribution having being regular, right? Being a regular distribution. So yeah, we will restrict ourselves to this case. And when you restrict yourself to that case, well, you have different results, right? So how is the class related to the ranks of the 2 form and the 1 form? Well, if you have that the class is 2r or 2r plus 1, then the rank of omega is necessarily constant, and it's 2r. So if you have one of these doublets, so the class is constant, then the rank of the 2 form is constant, always. If you have an odd class, then necessarily the rank of the 1 form is 1. So you have a non-vanishing 1 form, if you consider a doublet of odd class. And if the class is even, well, the rank of tau might not be constant. So the tau might be non-zero at some points or 0 at other points, right? And when here you have all these, like, you can try to think about counterexamples of things that don't work. In the preprint, we have a bunch of those. Here I give one. So imagine that you have constant rank of both the 1 form and the 2 form, then that is not enough to say that the class is constant. So it's a bit stronger in that sense. So for example, here, if we consider R3 with the usual coordinates x, y, z, it's here, then we can take tau equal dc and omega to be this. So if we calculate the kernels of these things, then you have this kernel here, and then for omega, you have that the kernel is generated by doing set minus set partial x, right? So this would be your kernel. And then, as you can see, so the kernels are always 1. The ranks are 1 for this, because the rank is the codimension of this kernel. So as we have 2, and the dimension is 3, the rank is 1, and for the other one, it's always 2. But the class is not constant, right? Because at set different from 0, then this is not inside this, right? But when set is 0, then yes, then we have this this inclusion. No, this inclusion, right? So if the ranks are constant, then the class might not be constant. We have sort of these things. But well, for the most part, we will just consider constant class, because as you will see, it gives you nice results. So, well, this is a bit like the most important, or one of the most important discussions. So how can we classify these pairs by their class? So as it turns out, what's important is the parity of the class. So as we saw, the class is the dimension of the annihilator, which is this thing here, right? But these are the dimensions. The dimension of these things are the respective ranks, right? And as we saw, we had very strong conditions on the rank of a 1 form and a 2 form. So as we saw, this, which is the rank of the 2 form, is always even, but the rank of the 1 form is always 0 or 1. So what this tells us is that if we want even, if we have even class, then we need this sum to not be direct, right? So the care of tau, it's not, the annihilator of the care of tau is not giving you new directions. It's inside the care of omega. It's the only way that the class will be even. And the only way that the class will be odd is if this sum is a direct sum, which is equivalent to this condition here. So in this way, we have kind of this classification of the two things, right? And then it will be also very useful to think in terms of these vector fields here. So actually, as I will show you, there's a theorem which relates this parity of the class to the existence of certain vector fields. And it's these vector fields right here. So if I consider a pair of a 1 form and a 2 form, then we define a Reeb vector field as a vector field which satisfies that contracted with the 1 form, it's 1, but contracted with the 2 form, it's 0, right? So this is like the usual, let's say, a generalization of the usual Reeb vector field you would find, for example, in contact mechanics or in cosymplectic contact manifolds in general. And then we have the Liouville vector field, which is a vector field that satisfies that when you contract with the 2 form, then you go back to the 1 form. So it gets you down to the 1 form. As you can see, this implies, just by contracting with the Liouville vector field on both sides, that the contraction of tau with the Liouville vector field is 0, right? So something that we think it's pretty visual to see is that these two vector fields, they cannot coexist. So if you assume that you have both a Reeb and a Liouville vector field for some pair of forms, then you reach a contradiction, because you can do this contraction here, and by definition, this is tau, so you get this here, and then by definition, this is 1. But also using the skew symmetry of the 2 form, you get this thing, and this contraction is 0. So you get that 1 equals 0, which obviously cannot be true, so you reach a contradiction. So these two vector fields cannot coexist. You cannot have both. Why? Well, because these vector fields are actually related to the parity of the class. So this would be like the main theorem of the paper, which is this theorem here, which tells you that the following statements are all equivalent. If we consider a doublet, which has odd class, then this is equivalent to this condition here. This is what we saw, just applying the annihilator on both sides. But remarkably, this is also equivalent to having a Reeb vector field. right? So odd class, if and only if you have a vector field. And for the even class, you have a similar statement, which tells you, well, you have these two equivalent conditions here. This is what we saw. Again, just applying here the annihilator on both sides. But this is also equivalent to having a Liouville vector field. So you get these two types of doublets, right, of pairs of one form and two forms, and they are basically classified if you have existence of a Liouville vector field or a Reeb vector field. So that's why, for example, you see Reeb vector fields in contact manifolds, but you don't see them in symplectic manifolds, right? Because as we will see later, they are examples respectively of odd and even class, right? So I just wanted to show you also that these vector fields, let's say this theorem relating the class to the vector fields, is useful also as not only because we're relating these dynamics to these pairs of forms, but also they are useful as technical tools just to prove things. So this is a characterization which tells you that a doublet has class 2r plus 1 if and only if you meet these algebraic conditions, right? So how do you prove this? Well, you can prove this with linear algebra, like you can take coordinates, you can do sort of these things, but you can also use the last theorem to reach contradictions if you assume that the other vector field exists. So this is what we do here. So I will prove just this implication. So if we assume that the class is 2r plus 1, then necessarily the rank is 2r of the two form. This is equivalent, as we saw. This is a famous theorem that you can find in any book that deals with these things. At the end, I will give a couple of references. This is the rank being 2r is equivalent to this condition and this one here. So we already have this. We only need to prove this one. But as the class is odd, then tau is nowhere vanishing. So this could happen, right? If it vanished, then we couldn't have it. And also, importantly, there exists a Reeb vector field by the last theorem. So if we assume that this is not true, then by contracting this expression with the Reeb vector fields that we know it exists, then we reach a contradiction because it says that omega r is 0, but we know that it's not 0 because the rank of omega must be 2r. And also, if you want to prove the converse, you can do a similar argument with the Liouville vector field, because these two conditions tell you that you have class 2r or 2r plus 1, and if you assume that the class is even, then there must exist a Liouville vector field, and if you contract it with this here, then it gives you that this must be 0, which is again a contradiction. So, I mean, these vector fields also, they prove useful just to prove different things. Using similar arguments, well, you can also give a characterization of when a doublet has even class. So let me just tell you that a doublet has even class 2r if and only if you have these conditions here. So as you can see, these are the two conditions of the rank of omega being 2r, and then this condition is similar to the one we found in the odd case, just telling you basically that the tau is in the direction of the omega, right? And then additionally, if you assume that tau is nowhere vanishing, so remember that if we had odd class, then tau must be non-zero, but if we had even class, then the rank of tau may vary. So it might be 0 at some points and not 0 at other points. Then if you have that it's nowhere vanishing, then basically you can take out this condition. If tau is nowhere vanishing, these two conditions already imply. Okay. And then if you put these two conditions together, if you combine them, then you get this result, which I've added here because in the literature you sometimes see conditions like this to define different structures. So if you have a pair, then you have the following equivalent statements. So if tau is non-zero and the class is 2r or 2r plus 2, then this is equivalent to omega having constant rank and these two conditions here. So as you can see, if you consider a one form and a two form and you just consider these two conditions, then they don't tell you that much because they don't tell you if the class is odd or even. And as you have seen, then these two cases are pretty different because you have different objects there, right? So you need to take that into consideration. You cannot just consider these two conditions because you're leaving out a little bit of information, right? And well, if these conditions hold, then you have the two cases. So if this is 0, then you have that the class is odd, and if this is non-zero, then the class is even. So well, these are just the last two propositions combined. And now let me tell you about the next section. Let's say it's about the geometrical objects that we can associate with these doublets, right? So the first one, and I would say the most important one, is this we call the characteristic tensor field. You will see why in the next slide. So the characteristic tensor field associated with a pair tau omega is the two covariant tensor field defined by this expression here. So you're probably familiar with this expression, for example, if you've worked in contact mechanics. So this would be, again, a generalization of that. So in general, this tensor B is not symmetric nor skew-symmetric. This is actually the symmetric part, and this is the anti-symmetric part, right? So this tensor field obviously defines a vector bundle morphism here, and you can extend it to work on vector fields. And its name is the characteristic tensor field because it's related to the characteristic distribution and hence to the class. So you have this proposition here, which tells you basically that the kernel of the induced map by the characteristic tensor field is just the characteristic distribution, right? And hence, just applying the annihilator on both sides, you have that the class is equal to the rank. This is what this is telling you here, right? And then this also proves the following conditions. Basically, if you want that B is an isomorphism, which is the case that we have in most geometries, you will see later in the example that basically if we consider any case that is, well, the cases that are most relevant, let's say in the literature, are those in which this is a vector bundle isomorphism. Well, this is equivalent to the characteristic distribution being 0 and to the class being equal to the dimension of the manifold. So basically, it's telling you if you want an isomorphism, then you need the class to be equal to the dimension of the manifold. So to be masked, because the class it's always, as it's taken as a codimension, then it's always smaller than the dimension of the manifold. Okay, and then another nice thing about the characteristic tensor is that it's also related to these distinguished vector fields. So you have these two propositions here, which tells you that if you have a doublet of odd class, then X is a Reeb vector field if and only if its image by B, it's tau. And also, if you have a doublet of even class, then X is a Liouville vector field if and only if its image by B, it's again tau. So as I've written down here, Reeb and Liouville vector fields are characterized as the elements of the pre-image, because this is in general not an isomorphism, but the pre-image of B with tau. So in this way, this characteristic tensor field gives you both distinguished vector fields at the same time, just as the pre-image of this thing. So this also tells you that these two vector fields are in a way analogous to each other, related to each other more, no? Then another interesting object is the extended characteristic distribution. We've called it like this, although in some papers, like in this one, you can find it just as the characteristic distribution. So it's this distribution, which is maybe a little bit less intuitive, but you will see that it's very similar to the other one in a moment. So it's basically the vectors which are in the kernel, such that when you contract it with the 2 form, they give back the 1 form multiplied by some number. Right? So this should already feel familiar to the definition of Liouville vector field. As we will see, it's related here, right? So if you have a doublet and tau is non-zero, otherwise, if tau is 0, then the Liouville vector field, if it exists, is also 0. So you wouldn't have this direct sum here, but well, it's just not very important. But if the class is odd, then this extended characteristic distribution is just the characteristic distribution. So it's not extended at all. It's the same, right? Because otherwise, if it had more things, then you would have Liouville vector fields, but you cannot have them if the class is odd because you have reps, right? And the class is even if and only if this extended characteristic distribution is the original characteristic distribution we described plus the Liouville vector fields, right? The span of the Liouville vector fields, which is basically what this is telling you. So either this is 0, this A is 0, or there's some Liouville vector field that it's generating you a number there, right? So this extended characteristic distribution is also related to the next object, which is the so-called extended three form, which is just you take your doublet and you wedge the two forms. So you get a three form, tau wedge omega. And the nice thing is that when tau is non-vanishing and the class is bigger than 3, if you don't consider these conditions, then tau wedge omega is just 0, right? If tau is 0, then the three form is 0. And if the class is less than 3, then by the algebraic conditions we had, then also tau omega will be 0. So those cases are not very interesting for this. But in the case that tau is non-vanishing and the class is bigger than 3, then you have this condition here. So the kernel of this three form is equal to the extended characteristic distribution, which at the same time is related to the characteristic distribution, right? So also this gives you a nice result, I think, which is that the extended three form is almost multisymplectic if and only if tau is non-vanishing and the characteristic distribution is 0, and this is equivalent also to M being odd dimensional and the class being equal to the dimension of the manifold.
Okay. Sorry, question. You have considered the so-called kernels of first order. There are other kernels, for example, for the omegas and things like that. Have you tried to take a look at that?
Yeah, that's a great question, and it's actually in the further work part. It's a great question. So, like, one of the things we're trying to think about also with Ruben, I don't know if he's here, I think so, is to generalize this framework to n and n plus 1 forms. So to more general forms, so just consider a pair of forms. And then I believe that there, the kernels you're saying of taking multi-vector fields will play a part, for sure.
Okay. Yeah, because I have seen construction like this for differential systems because they are used to be defined by means of kernels of one forms and two forms, and things like that, or even higher. So it could be nice to know it.
It's very interesting.
Everything you have done so far, as much as I see, is linear algebra indeed. I mean, you have tensor fields and things like that, but the relations between the kernels and all this stuff is rather punctual, at every point.
Yeah, totally. Like the only thing that it's, I would say, not linear algebra, it's just this theorem, which if you want to prove that the Reeb vector field is smooth, then you need to do some stuff. But at every point, this also holds. It's like the only thing that it's not, let's say, linear algebra, it's that. Yeah.
Because I will tell you that something that is also interesting in certain theories is the structure of the set of the rank of the kernel. When you have, for example, intersection of kernel eta and intersection with omega, it will have a structure, and sometimes this structure is such that the set of points where the rank is 0, rank 1, rank 2, whatever you have for higher order, you can make some characteristic distributions, and depending on the rank, you can divide the total space into certain subspaces. So studying this is also interesting, but it's more in the direction of doing this at several points. Okay,
this is
thank you.
Related to like flags of distributions and stuff like this last thing you said.
I mean, it's related, for example, with integrable systems. The differential equations, they
Okay.
have associated certain families of differential form, yeah, that boost
Mm-hmm.
structure, things like that. They have one form, they have two forms, and you have to study these forms, yeah.
Mm-hmm.
And the kernel of these one and two forms, the intersection of the kernels, they have a certain structure, yeah. It's not clear if they are manifolds or they are stratifications or they are things of this sort. So sometimes it's
Mm-hmm.
interesting to know it. So, okay,
Mm-hmm.
thank you.
Oh,
That's
thank
nice
you.
comment.
So yeah, I was just gonna say what almost multisymplectic means if someone doesn't know it. So also almost multisymplectic means that the map induced here is injective. That's what almost multisymplectic means. In general, if you have a P-form, almost multisymplectic means that the map just contracting by a vector, it's injective. So we have basically characterized all three forms that are multisymplectic, which are written like a one form wedge, a two form with this. Okay, and now after these results, what I would like to tell you about are just some examples that you might be familiar with. So I will be talking about presymplectic systems, well, symplectic and presymplectic systems, Hamiltonian systems, presymplectic systems, locally conformally symplectic manifolds, and also precontact forms, right? So, okay, let me start. I will be giving the definitions, although I know that many of you know these things, but I will just be fast with it. So a symplectic form, as you know, it's just a closed form, and which is a closed two form, which is non-degenerate, right? So that the kernel of this two form is zero. So in this case, well, you can always consider the doublet, which takes as the one form just zero. So there you have a doublet. And then this doublet has class 2n because this kerr omega is zero and the one form is not doing anything. And also as this characteristic tensor field, well, you have the usual isomorphism that we use in symplectic manifolds. And then as the one form is zero, the Liouville vector field is just the zero vector field. Another interesting thing you can do is if this two form is exact, so you have an exact symplectic manifold, as you might have, for example, in the cotangent bundle of any manifold, then you can consider the doublet, which also takes the one form, which the potential, and then this also has class 2n. As a matter of fact, if you are in a manifold of dimension 2n and you want class 2n, then you will need a non-degenerate two form always. But then, as you can see, this B changes, right? So the characteristic tensor field changes, but it's still an isomorphism. You can take this different one, and the Liouville vector field is the one here, and it's just in this case it's an isomorphism, so it's unique, and it's the pre-image of the one form, and it's also equal to the inverse with the isomorphism induced by the symplectic form.
By the way, sorry, Angel, a
Yeah.
question, because you know when you have this beta hat, yeah, it's
Yeah.
indeed a two covariant tensor, yeah?
Mm-hmm.
Yeah. Have you understood this like just a linear mapping? I mean, looking for the signature or things like that of it?
Yeah, so we are actually with Ruben right now working on a more general study of this, then like just getting a two covariant tensor field, which is non-degenerate in the sense that it induces an isomorphism,
Yeah,
and you
yeah,
like study it in general. In
yeah.
particular, this is in the further work also, I will explain it, but we're gonna apply it to calculate different brackets. So for example, when you take a symplectic form, then you have a Poisson bracket. If you take a contact form, then you have a Jacobi bracket. So the relation between them is that, well, you have this non-degenerate two covariant tensor field that the bracket comes from. So how can we relate them all? How can we? And
Because
this involves the study of these bilinear forms more in general.
indeed,
Yeah.
I will tell you that I met something very similar to this. I was studying first time weird problems with one of the attendees in the conference with Pavel. It was about a two covariant two covariant tensor field, yeah, and it appears in certain models, for example, when you have relativity and electromagnetic fields and things like that. It was very similar to this B hat, yeah. You only that you have written it in another manner, yeah, like amorphism and tangent cotangent, and it was interesting to me to look for the properties of these things because they could be related to physical systems, yeah. It was certain things like, for example, when it has the B hat, you can make the transpose of it, yeah, and you can compose them to have certain morphisms from the TM to the TN, for example, or the T star M to the T star M, and you have the endomorphisms, and to understand the eigenvalues and things like that, yeah, in these cases.
Yeah. We've seen some, like we've been reading some stuff, and to like these bilinear forms are classified by doing that. You take the transpose and then you compose it with the inverse, and you get an endomorphism, and you study the eigenvalues of that, and that gives you like a classification of these
Yeah, some of these
two
results,
covariant tensor fields.
yeah, I are studied, but I was interested in how this could be used, for example, in physical systems as well. You pick up a certain Riemannian metric is a symmetric part, and then you have a certain electromagnetic field that is antisymmetric, and how you you add them together, and you get something like the B hat you had, only that in the version that it is a bilinear form. There is one part, indeed, in this B hat that is related to antisymmetric part, as in the contraction with the symplectic form. You have another one that is symmetric, that is the contraction with the one form, yeah? And pretty much describe certain other systems I was looking for. Also in dissipative systems, for example, they are related to certain tensor fields in which you have a certain symmetry and antisymmetric part like this. So it would be interesting to see the relation. Okay.
Yeah. We believe that it's very interesting, and also like one of the driving points, let's say for us, is that this work also gives a lot of attention to this two covariant tensor field. Like we thought it was very interesting to see that it played like a big part in this study, let's say.
Okay.
So yeah, thank you for the comment.
Okay, so it seems that I've found a connection with something that I was interested in. No, thank you. Please go on.
Okay, thank you. And well, then I was just explaining more examples. So from symplectic geometry, we can go sort of naturally to presymplectic geometry. This is just relaxing the rank condition. So just let's take a two form which is closed, but it's not non-degenerate. So in particular, we consider that the rank is constant. There are some places where people consider that the rank can be whatever, but we consider that it's constant, so that in particular we can have constant class. And in this case, you could still consider the doublet with the zero, and the class will be just equal to the rank, right? And in this case, the Liouville vector fields will just be the sections of this kernel. Also, again, if omega was exact, then you could consider this pair. But here you have to be a bit more careful because that might not be a doublet. So the class might not be constant. Right? So there you have to be a bit more careful. Another interesting example would be Hamiltonian systems. So a Hamiltonian system is a triple where you consider a manifold, a symplectic two form, and a function, which is called the Hamiltonian of the system. And you can also generalize this to presymplectic geometry. So this two form, instead of picking a symplectic form, you pick a presymplectic form. That's what you find, for example, when you consider singular Lagrangians, you get a presymplectic form. And then the interesting thing is that when you're considering these systems, normally you're interested in the dynamics. You're considering Hamiltonian systems, and you're interested in the Hamiltonian vector field, which is the vector field that you get from this equation. But if you now put the lenses of doublets of what I've been explaining you, then the Hamiltonian vector fields can be thought of as the Liouville vector fields of this pair right here. So this is telling you, well, the Reeb and Liouville vector fields are not just vector fields related to the pair, but they can also be vector fields which have dynamical significance. Well, we already knew this because if you think about contact forms, then you have that also. The Reeb vector fields are important also dynamically, but here it's also very clear. And yeah, just as a comment, when omega is degenerate, so when you pick a presymplectic form, let's say, then you have this problem that the Liouville vector field might not exist. And this is what brings you to the theory of constraint algorithms and stuff like this. When you consider singular Lagrangians, you get a lot of this. And just as a comment, notice if you know a little bit about this, then the first step of the constraint of the presymplectic constraint algorithm would be to try to solve this equation, so because you need the dynamics, and to find the points where this holds. So that would be calculating the first constraint submanifold. Then that's the same as asking that the class of this pair is even. So as you want a Liouville vector field, you can only have a Liouville vector field if the class is even. So you can like give this different interpretation to the constraint algorithm, at least to the first step of saying, okay, I'm interested. The first constraint submanifold is the set of points where this pair of forms has even class, right? So we believe that that was interesting. And then we'll be giving more examples. Yeah. So for example, you can have cosymplectic structures. Cosymplectic structures are just pairs of a one form and a two form again, but now both are closed. And then you have this volume form. By the algebraic conditions we saw, this volume form is having this volume form is equivalent to this pair having odd class. Again, as the class is having odd class equal to the dimension of the manifold, which must be odd. Again, because the class is equal to the dimension of the manifold, this two covariant tensor field is again an isomorphism, which is something you find in cosymplectic manifolds. And then, as you have an isomorphism and the class is odd, then you have a unique Reeb vector. And in this case, as tau and omega are closed, then the three form here, the extended three form, is not only almost multisymplectic, but it's also a multisymplectic form, which means that it's closed. The three form is closed. With this, you could also
one question,
yeah.
Ángel. It's a multisymplectic, but does it have any interesting property about multisymplectic? Because there are lots of them. I mean, it's related to some kind of particular case of multisymplectic form. It's related to physical problems or whatever.
I mean, I'm not sure I can tell you that it has some significance. What I can tell you is that I believe that we could that you could, for example, write the equations of motion using these three forms. So if you have a cosymplectic manifold and you're interested in time-dependent Lagrangian mechanics and you want to write the equations of motion, then you can either do it in the usual way with the Reeb vector field and stuff. But I believe you can also write them using this three form, for example. So I don't know if that would be like a kind of interesting physical thing, but
related symplectic forms, we know the structure is always interesting. But I would like to, well, I wanted to know if there is anything else.
Yeah,
okay,
yeah.
Thank you, Ángel. Thank you.
Well, we just put this kind of because, well, you have it, and it's interesting, I think, that you have this multisymplectic form, and also it's not something that is used very much because we're not very used to using three forms. I believe in general, but it would be interesting to exploring the applications of this. And well,
I would say also this approach is useful if you want to generalize these definitions beyond standard ordinary finite dimensional manifolds, because the standard definition of contact form or cosymplectic structure as you presented, they rely on having a volume form, which is something that doesn't exist, for instance, on supermanifolds or in infinite dimensional manifolds. But instead, if you use this type of constructions that you are presenting, that rely on some map being an isomorphism, that idea more or less naturally can be extended to more general contexts where the notion of volume form in the usual sense doesn't exist.
Yeah, that's a nice comment that you I think I commented this with Fraser that was here also. I saw that, well, when you have this, you're dealing with infinite dimension, then you don't have these volume forms, you don't have these notions of having equivalences of different things. You can define them in different ways. It's very nice. So for example, you could say, well, the characteristic distribution being zero gives you very nice structure. So let me generalize this to infinite dimensional where zero makes sense, but having this volume form doesn't. Right? So, yeah, thank you, Sir, for the comment. And well, I will just be fast with the example. So you could consider precosymplectic forms. These are just, again, a generalization of cosymplectic structures where you consider closed forms, but now you don't ask for this volume form, but you ask for the class to be constant and tau to be nowhere vanishing because, well, we're thinking about the typical cosymplectic case where tau is just dt, right? So you would want to keep that. So the closeness, as you can see, has an appeared match. So this is in line with, well, we're dealing with multilinear algebra more than with manifolds, let's say. So this closeness condition doesn't come as often, but this closeness condition, for example, gives you involutivity of the different associated distributions you have. And that could be useful, for example, to prove Darboux theorems and to give some other results, as you will see later if I have time. I have some results on this. And then just as a comment in the literature, for example, in the paper you have with Xavi and where you look for Darboux coordinates when you consider precosymplectic structures, you only consider precosymplectic structures which have odd class. Why? Well, because for example, in the equations of motion, when you are dealing with cosymplectic Hamiltonian systems, then you need like a Reeb vector field to write those equations of motion, or at least it seems like that. So you're like, well, I don't want these precosymplectic structures to not have reps, so I will just restrict myself to having reps. And this also gives you this odd class, and this also gives you a Darboux theorem. But what I believe is that, well, you don't need to restrict yourself to just that case. You can also work with the even case, and just taking into account that now instead of this Reeb vector field, you have this Liouville vector field, right? And so here I've written a few written examples of precosymplectic forms. So if you're in R4, then you can consider this one form and these two forms, and you can check easily that that the class of tau omega 1 is 3, and the class of tau omega 2 is 2. So these would be examples of precosymplectic structures of odd and even class. And well, you can also calculate the Reeb vector fields and the Liouville vector fields. I will go a bit fast because I'm running out of time. But well, this was just to say, okay, we can give some calculations here, and they're pretty easy to do. Another example would be locally conformally symplectic forms, where you have two form that is non-degenerate, but it's not closed, but it can be closed locally with a function. So there exists some function such that when you multiply it by the two form, its differential is 0. So you like close a form. This is equivalent to the existence of this closed one form, which is sometimes called the Lie form, which tells you that when you differentiate the two form, then you get this three form here. So again, you could consider a doublet which takes into account this Lie form and this two form. The class of that would be 2n because omega is non-degenerate. And again, you can consider Liouville vector fields. You have this isomorphism. And well, this is just an interesting remark that notice that this d omega, just because of the definition of locally conformally symplectic, the d omega is minus the extended free form. So they are related in that way in locally conformally symplectic manifolds. Another example is contact forms. So when you have a contact form, you have a one form such that this is a volume form. So this is telling you, well, in contact manifolds, what you care about are pairs which are of a one form and its differential. right? So the usual notion of class, for example, that you can find in the book by Cote-Billon, there the class is considered just for pairs like this, just for a one form and its differential. But I think also the nice thing about this paper is this generalized notion of class that works well with any pairs of forms, right? So in contact forms, you would care about the one form and its differential, and well, the class being a contact manifold is equivalent to the class being 2n plus 1. Again, because you have this class equal to the dimension of the manifold, you have this isomorphism. Because the class is odd, you have this Reeb vector field, which is very important. Also, in this case, this is an almost multisymplectic form, not necessarily closed. But yeah, you have kind of these things. What was useful for us about this framework was being able to construct this definition for pre-contact forms, which is, okay, let's generalize contact manifold just by taking an over vanishing one form and asking for this pair to have constant class. This is not necessary. This does not necessarily hold always, but yeah, you have this definition, and then you can classify them by odd and even class. So before in the literature they just considered this case, right? So there are works done just considering this case here, but let's say that the new thing would be just, okay, let's also consider the even case because it's interesting and we can deal with it just fine, right? So well, here I've written an example of pre-contact forms. So if you consider, I don't want to delve into the mechanic part of it, but if you consider some contact Lagrangian, then you can get some one forms which actually have even class. So this was not considered much in the literature. This case was like thrown away a little bit just to have like Reeb vector fields and stuff, which seem to be important, but I don't think they are as much always. I think you can deal with these structures as well, and you can find these one forms which have even class, and that's fine. So yeah, I'm running a bit low on time. This is like the last section, so I will try to be fast. So on the line of what I was telling you, so in the literature, you have these works where they only consider odd class of per-contact forms, for instance. So our question was, okay, let's say throw away these ideas that are there. Let's try to find a way in which we can go back to the odd case if we want. So the idea would be, okay, let's take a doublet of forms and let's try to find a transformation which changes the parity of the class. So if I want odd class, I can have it just by, for example, multiplying by some function or doing some transformation to that doublet. Right? So this is a little bit the motivation here. So if you have a pre-contact form and you rescale it by a function, then the kernel is conserved. So if you're thinking about contact or pre-contact manifold as these distributions of different ranks, then that is conserved. But the underlying structure, the one form structure, let's say, is not conserved. So the reps might change. You can also like not have reps anymore, right? Why? Because when you're doing this change, multiplying by a function, you're basically changing the doublet in this way. So you're not multiplying the doublet by a function, but you're also adding this part here, which might give you some problems. It might modify your structure in a non-trivial way. So our way to deal with that was consider transformations of this type. So you start with some doublet with tau non-zero. We will consider this from now on, tau non-zero. And then you consider an additional one form, and then you study the class of this transformation. So you just sum to the two form this wedge of the new one form with the other one form. And well, just as a comment, this generalizes the thing that you would do in pre-contact or contact forms of like multiplying the one form by a function and still having a contact form, just because if you consider this change, then as you can see here, the term that we added appears, right? So this would be just one of these transformations with alpha taking df, the differential of a function. The other change, well, here you have this multiplication of everything by some function, but this is not a problem because the transformation above is a bit more complicated than just multiplying both things by a function. Because if you take a doublet, you multiply it by a nowhere vanishing function, the two form and the one form, then, well, this is not a problem because if the class is constant, then this will also have constant class. So if you have a doublet, you will get a doublet. And the characteristic distributions will be the same. And also the Liouville and Reeb vector fields are related to each other. So these type of transformations are not a problem. However, the other ones, they might change their structure pretty heavily. This is, however, a lemma that tells you, okay, it's not that crazy. So if you have a one form and a two form, and you want to see how the extended, well, and you want to do this transformation of adding this thing, then your extended characteristic distribution doesn't change. So that's preserved. And this already tells you a lot of things. So for example, if you have a one form, and then if you have this doublet and then this other one, then the extended three form they define is the same. Well, this is obvious. But also from this result, you have that if the class of this was 2R or 2R plus 1 or 2R plus 2, then the class of this will also be 2R plus 1 or 2R plus 2, just by the definition of characteristic distribution. So this is telling you that if you consider one of these changes, then the class either stays the same or it changes by 1. Okay, and it can go from 2R plus 1 to 2R plus 2, or from 2R plus 2 to 2R plus 1. Those are the only changes you can
Ángel,
find. Yeah.
sorry, yes, a couple of comments, okay?
Sure.
And so unfortunately, I must to leave now, but Xavi will be in charge. But I wanted to tell you something. First, your word, I said, just it's the B form the B map you describe, for instance, yeah, you can put it like a covariant tensor field. In such a case, it's interesting to describe its properties related to Hamiltonian vector fields of the related structure, pre-compact, more symplectic, and things like that. It could be nice to know it. Another thing is that the relation of this structure to multisymplectic can be used to associate the reduction of theta in this structure, like almost symplectic, and that with associated multisymplectic structures, what is also interesting. Yeah. Other thing that I wanted to tell you is physically there are dissipative systems. They are described by means of things like the B you described, that they can be put in this manner. So it would be interesting to understand the properties of this mapping in terms of this. And in general, I could say that it could be nice to understand more in detail the properties of the physical systems related to these structures. This is my opinion. Okay, so this is what I wanted to tell you, but quite surely I will cite several view results because I think I use it. So thank you.
Thank you very much.
And
thank you very
take
much.
the time you need it. Okay, Xavi will be in
Okay,
charge.
thank you. Thank you very much.
Thank you.
Thank you very much. Yeah, so I'll try to be quick. There are a few slides left, but just commenting on these changes. So that the class might change, as I said, it might stay the same or it might change by 1. So we wanted to characterize these changes in case you wanted to do one. So the first part would be, okay, I have an even class doublet and I want to go to an odd class doublet with one of these transformations. How can I do it? Well, as it turns out, the condition for that is very nice. So if you start with a doublet of class 2R plus 2, then the new doublet, the transformed doublet, will have class 2R plus 1 if and only if you have this condition here with the Liouville vector fields. So the contraction with the one form by any Liouville vector field is -1. So this will be very useful, as you will see, to prove some results. First of all, I wanted to comment that, for example, if we consider the case of alpha being the differential of a function, then this type of changes might not always be possible. So, for example, here's an example. So you take this manifold R4 with the usual coordinates as x, y, z, t, and then this one form, this two form here, and you can calculate the kernels. You can calculate the class of everything, and then the class is even and it's equal to 2. So in principle, we could go down to class 1, right? And so, okay, the Liouville vector fields are this one, plus the things that are in the curve of omega. And then what you would need to do is find a function, right? Remember, because we're just considering the case of these things, find a function that satisfies this for Liouville vector fields. This gives you a system of linear PDEs, this one here, which cannot be solved. Why? Because, well, if you put this -1 and this -1, and then you do the mixed partial derivatives here and here, then you get that they need to be different things. So this has no solution. So just as a comment for us, was interesting to see when this multiplying, well, this transformation by a function could be doable and when it couldn't be. So the next result gives you sufficient conditions for these functions to exist. So if you have a doublet of class 2r plus 2 and tau is nowhere vanishing, and you have these two conditions here, which are that the characteristic distribution is integrable, and that for every Liouville vector field, when you do the Lie bracket with something from the characteristic distribution, then you end up in the characteristic distribution again. Then this is enough to have a solution locally. So for a function, an nowhere vanishing function to exist, such that this transformer pair has constant class 2r plus 2, 2r plus 1. And this, for example, is satisfied in the precontact case. So in the precontact case, these two conditions are satisfied. So if you're in a precontact manifold, you can always find a function such that locally, at least, you can go to odd class if you need to, right? So well, here there's an example of something that's been going around a little bit, which is this contact Lagrangian being PS. So if you consider this simple Lagrangian, then you get a one form which has even class, right, with its differential form. And then you can calculate the Liouville vector fields. They are these ones. And if you want to find a function such that you go back to class 1, so you get something that's odd, then you need this condition here, which translates into this PDE. And then you can take, for example, this solution here, and then you can check that indeed the new form, which is this one, has class 1. You can check it because, for example, it's exact. Class 1 for precontact forms is equivalent to being closed, to being exact. Okay. And then the other result, we've seen how to go from even to odd, and now we'll see how to stay odd. So if you have an odd doublet, what transformation can you do that lets you stay odd, right? So here, as I say, preserve the odd parity. And if you want that, then your one form must satisfy this condition here. So the contraction by anything that it's in the characteristic distribution should be 0, right? And you have a similar result to this last one to ensure conditions for these functions to exist. For functions, so we're taking again this thing here, for one forms formed by functions to give you this preservation of a parity in this case. And in this case, well, by the Frobenius theorem, it's enough to have the characteristic distribution to be integrable, right? So yeah, I'll just finish here, just some further work that we've been working on. Some of this has come up during the talk, but well, we're applying this framework to deal with singular Lagrangians, both for action-dependent and non-autonomous systems. For non-autonomous systems is something that we're already working on with Daniel Torres and also with my thesis advisors, because as you probably have seen, this framework shines mostly when you're dealing with structures that don't have the maximum class possible, which are the usual ones. So for, let's say, degenerate geometric structures that you might find when you deal with singular Lagrangian and stuff, and it was our motivating examples to start studying these things. Also, as I commented before, well, we're using these things to study brackets in more generality. So give me a doublet, and I'll tell you if it gives you some kind of Poisson or Jacobi bracket, and also use this framework to generalize how to yield a bracket from a pair of forms. And also, this has led us to the study of these two covariant tensor fields more in general. This is something that we're working on right now with Rubén Izquierdo and Manuel de León. And also the generalization of this framework to deal with pairs of n+1 form, which is something that we're also working on with Rubén and Manuel de León. And well, we think that this is very interesting, for example, for field theories and for the multi-contact formalism or the multi-symplectic formalism. And yeah, we're trying to deal with that, and there we think that that these kernels with multi-vector fields will appear, as Javi commented before. And well, another point that would be interesting, we think, is to study more generalized doublets, even where the class might not be constant. So what happens when the class is not constant, and what can we still say, what can we not say? So you will get like some singularities, some stuff that will be a bit harder to deal with. So maybe this would be a bit more topological work in general to deal with stuff like this. But we think that it would be very interesting because normally we just consider this constant class case. But when you're dealing, for example, with singular Lagrangians, you might not have constant class. So it's an assumption we, let's say, put that it holds in a lot of examples, but in some others, it might not. Right? And then, well, just to finish, here are some of the references. This is the preprint I explained, basically. So this whole talk was based on this preprint we published in February. And then just as a couple references that were very useful to us, is the book by Godbillon, and then the book by Lieberman and Moll, where you can find some constructions similar to this one and some results and some nice stuff. So yeah, thank you very much. That's all.
Thank you, Ángel, for your talk. Are there any questions or comments? No? Okay. Well, thank you again, Ángel, and see you all next week. Next week we have a special session where some students will practice their defenses, their bachelor thesis and master thesis defenses. So see you all next week. Bye.
Thank you very much.
Xavi, ¿te puedo